Okay, here's my chance to look for non-academic jobs. Hello? I'm here for the interview?
You're fired! I mean, hello. Hello, have a seat. Have a seat.
Yes. Okay. Thank you for seeing me and taking a look at my resume. Hello? I'm here for the interview?
Why don't you tell me a little bit about the work that you do?
Well, the primary focus of my research has been a team effort to make thin film electrode substrates, catalysts for water splitting, CO2 reduction, hydrogen production, oxygen reduction, and cold fusion. The primary focus of my research has been a team
all in
effort.
one?
Yes, all in one. It's a 30-layer thin film electrode that takes about 2 weeks to make.
And how long does it last?
Cold fusion. About 5 seconds, which is enough time to get data.
Oh, I see. Well, postdoc, your resume is very impressive. Do you know what we do here at Energy Electrode Film Research Tech Incorporated?
Yes, you make electrode films for energy research technology.
Bingo. And we employ researchers like yourself at our state-of-the-art facilities. Tell me, in your research, what layers of the film do you make?
I make the 9th and 10th layer in the process.
Well, what if I told you you could put the 9th, 10th, and 11th layer in the process?
Oh, that would be amazing. I'd be honored.
Well, I think you've got what it takes to work here. You'll probably also need a HR phone interview, a technical phone interview, a secondary follow-up technical phone interview with management. You'll have an on-site interview. You'll also need a drug test, background test, abstract submission, peer review, and that'll be it. So I'll see you in about a year.
Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
All right, everybody. Hello, and welcome.
Hello, everybody. Can you please in the comments, could you let us know if you can hear us? That's one of the first things that we do is just a sound test. And we're very excited to be here. We got a lot of questions, which is great. Before we begin, I'm just going to read through a couple things, just some basic introductions. Welcome to our 4th episode of what we call Echem Office Hours, or Ask Us Anything About Electrochemistry. Just a few things to note is that we're just going to answer questions that come in through the chat. If you have a question, please ask it in the chat. We typically will prioritize YouTube members. And speaking of which, thank you for all of you who are YouTube members of our channel. We really appreciate it. We are using Zoom as the broadcast platform for Ask Us Anything About Electrochemistry. We have found that there may be a 20-second delay between what you see from us and what you type in the chat. So typing in the chat is instantaneous, but what you see will be delayed probably by 20 seconds. So just keep that in mind. We also just want to state that electrochemistry is a very difficult subject. There are no stupid questions. We may or may not be able to answer them all, but this is a safe venue where you can ask any questions you want, okay? We're going to aim for this to be about maybe 1 to 2 hours. It could go longer if there are a lot of questions and there's a lot of engagement, but generally that's what we're aiming for. And lastly, we're going to apologize in advance if we mispronounce anybody's name. So just letting you know that.
Yeah, that's not an if, that's a when.
Yeah, that's right.
But, yeah, well, thank you everybody for being here. As Alex said, I'm Neil Spinner, your other co-host, and thank you for those who have put questions already. We're not always sure if we're going to get preloaded with questions here when we start, but I actually wanted to answer one question from Shrib. See, I told you I'm going to mess up a name. Shrijib, I think is how it's pronounced. I see that you had asked a question. There's a previous version of this. Yeah, it's just a technical thing. It's not interesting. But anyway, I see that your question, you re-put it. I remembered what you had asked in the previous event, so I want to answer that for you. So the question is how to plot one CV curve, let's say the 6th one among 10 CVs using our software. So you're using a WaveDriver 100 and our Aftermath software. So first of all, thank you, appreciate it. I'm going to share software. This might be a slightly different version. Make sure I've got the right one here. This might be a slightly different version than you're using, but it's same sort of thing. Here, let me get a little invitation. All right. So here you see, for example, a bunch of CVs. So there's a couple of ways you can do this in Aftermath. So the quickest way, I think, at least for me, that I'd like to do, first is what I'll do is you can delete stuff, but it's irreversible. So you don't want to, delete, parts of your data and then wish you hadn't later, right? So let's keep that out of the way first. So the first thing that I usually like to do is just make a new plot. Okay. So so in this case, like this is like glassy carbon disc CV, right? This is just some other data that I'd taken previously, but you can see I did a CV. This is like ruthenium hexamine, so it's a nice looking duck, and it looks like I did like 4 or 5 total CVs, whatever it is. Let's say I want to take one of the middle ones. So what I can do is right click and go to select points. You see what's going to do? It's going to pull up this this dialog box here. I can pick all the segments. So when I start selecting them, you'll see that it highlights them for me, right? So here's segment 1, segment 2. So what I'm really just going to do is pick, if you want the 6th segment, for example, well, 1, 2 is 1, 3, 4 is 2, 5, 6, 7, 8, 9, 10. So like in my case, let's say I have 1, 2, this is segment 1. All right. Segment 2. So let's say I want segment 3. So that'd be segments 5 and 6. So I want CV3. Words are hard. And then so I want segments 5 and 6. So this is the CV that I want, right? I'm going to select these 2 segments, click OK. And then I'm just going to hit Control C or I can right click and hit copy, come into the plot, click here, Control V, paste it. So there you go. There's the one CV that I want. So that's one way to do it. The other way, simply open up this here. You see the tabulated data. Okay. So here's the tabulated data. I'm going to open an Excel sheet. You won't be able to see it till I share it with you. Just a moment. So there's 2 ways to do this. Okay. One is that this is the tabulated data. You see that it's shaded blue. And then if I scroll down, it's pink. It'll alternate. So this isn't like the exact easiest way, admittedly. Okay. Because you have to sort of remember where you're at, how many have you gone by. Okay. But what you could sort of do is find, okay, well, I did blue, pink. So this is like the 3rd set. I could just sort of highlight here. And I could like scroll down until the end of the next pink segment. These are set, the color coded by segment. So I could copy those points like that. So let me see, there's where the pink segment ends. Hold Shift and click down here. And then again, Control C. And then I could also click in here and paste it. You see, when I go to paste it, it's going to ask me what the units are because I just copied data points. So actually what I'll do is I'll just select, see, x-axis is potential. Where's potential? So this is a bit of a different sort of path here, right? And then current. And if I paste it here, well, it's the same trace. But anyway, so there you go. So that's another way to do that. Now I just copied those points. I can also, let me just do one other thing here, just show you. So I copied them. Sorry, let me come back to Aftermath real quick. The other thing I can sort of do, which if you're not aware of how easy this is, if I want to get the whole data out, I can just click on this trace and just hit copy points or Control C, right? And then what I can do is go to, I'll show you Excel. When I come into Excel and just Control V and it just pastes. So that's just the data right there. So that's like a quickest way to get it out. Now, this would be, if you want one of the CVs, you would have to do it in Excel and sort of, plot it and figure out, exactly where in Excel. So now you have another sort of a job on your hands, right? To figure it out where the data is. But if you prefer to work in Origin or Excel or something, that's a way for you to sort of extract the data out pretty quickly as well. Let me know if that doesn't fully answer your question. I hope that kind of does it for the most part, though.
Okay.
As it relates to selecting a single trace when you have a bunch in Aftermath. I thought I'd get that answered for you quickly.
That's good. So we have a lot of questions coming in.
Yeah, let's get
to it. One question, just kind of going through as quickly as we can.
Mm-hmm.
One question from Survivor Stu. Again, sorry for any mispronunciations. Survivor is talking. He has a job interview coming up. He wants to know how to deal with flow batteries and if there's any chance we can cover them. Neither Neil or myself really have very much experience with redox flow batteries.
Yeah.
I think from a interview perspective, something that at least maybe we can both share a little bit about our experience, but I would make sure you understand some of just the fundamentals
Like the Nernst equation is very important for understanding how redox flow batteries work. What is the potential and the potential difference between both sides of the flow battery, the cathode tank and the anode tank or anolyte tank or catholyte tank. Getting some information and knowledge, reviewing different types of membranes and how that works. So I don't know what exact type of job you're applying for, but I would familiarize yourself with just just know a little bit more about the company or the organization is also very important. But unfortunately, I don't know, Neil, if you have any things you want to add.
Yeah, it really is those basics. So I mean, I obviously, without knowing more about your specific company you're applying to it, I'm not asking for that, to be clear. I don't want to have you divulge information that perhaps you can't or you prefer not to. I'm not asking for that. What I am saying is that without knowing the specific company and perhaps what they maybe have requested of you in particular, what I can say is that if you have training in electrochemistry or some knowledge of electrochemistry, I would say hopefully, I want to say likely, but I don't know that that's the case. I would say hopefully that if they're going to hire you for your knowledge and expertise in a subject, presumably you would be able to learn about it given your like general electrochemistry knowledge, right? I mean, how much stuff have we had to learn about since we've been hired at Pine that like corrosion or even like you're a spectroscopist. I don't know. I didn't know anything about spectroscopy.
Yeah.
I still don't, but I'm pretending to for my job. So, but anyway, the point is that I know electrochemistry. I, got a PhD and a postdoc in electrochemistry. And one of the ways like Alex, just to sort of, support what Alex said is that you can express your knowledge of the concepts of electrochemistry or the basics or things like that, and at least read a little if you can before your interview about some flow batteries or about what the company does, what it specifically makes or researchers or whatever the type of company it is. Those things will go far. And the most important thing I would say really is do not lie.
Yeah.
Do not lie and pretend that you know more than you do about something. You would be surprised at how far honesty will get you. If they're asking you a question like, do you know about what potential should this be at, whatever, you just say, don't try to make up an answer if you're not sure. I'm sorry, I don't know the answer to that question, but I am confident that if I have the resources and the time and, I will be able to learn the specifics of the, products or the whatever that the company is supplying, something like that. But you just don't want to pretend. That will come back to bite you almost for sure.
Yeah.
I don't know if you have more than that, but
Stu commented, he says Survivor, part of his name is a Pokemon. So I haven't played Pokemon in a very long time.
I don't know anything about Pokemon. So.
But Stu will I think he's asking for a little more information about like the Nernst and Tafel equations.
Yeah.
I think we will do that, but we'll do it later. So stay tuned. We're getting a lot of questions in pretty quickly. So I'd like to answer some of the other ones relatively quickly. Some of them can be answered quickly. Some of them will take some time, but stay tuned. I think going over, I think the Nernst equation, at least, is one of my favorite equations to go over because there's ways to think about it that are different. But we'll come back to you in a minute. Let's answer Salah's question about, and actually this is related to Prashant's question also about electrochemistry books. What is a good book you can recommend for learning the fundamentals of electrochemistry? So I know, Neil, you brought this book down.
I did. Yeah. So, I mean, there aren't, to be honest, like a huge number of textbooks on electrochemistry, or if there aren't a huge number that are like widely accepted, but on like general electrochemistry, this is your best bet. So this is like, some people call this the Bible, if you will, the electrochemical methods, fundamentals, and applications. So we're on the third edition. This is really quite new, actually. Barden Faulkner and then Henry White from University of Utah, right?
Yeah.
He was obviously, as you can see, involved with this edition. The the second edition was the one that most people have had for quite a while. I know this has been a long time coming. This really goes into all of the details that you would need to just learn very basics of electrochemistry. You're going to have to read, literature or come to amazing YouTube events like this to maybe get some more specifics, right, about applications. This is really more of a fundamental of electrochemistry. Obviously, there's specific examples because it's a textbook, right? But it's, if you want to really get in-depth knowledge of how oxygen reduction reaction or lithium-ion batteries or spectroscopy works, this is not, the textbook exactly for you. The last thing I wanted to say about Barden-Faulkner textbook, to brag on Pine for a moment, is that we're developing simulation software. And so actually you can see over there, right? So courtesy of Pine Research. So some of these plots in here, we have a simulation software that we're very close to releasing. And anyway, actually even the plots on the front here, these were done with our software. So not to brag, but I'm unashamedly bragging and plugging Pine a little bit here. Sorry, not sorry, but yeah, we're pretty proud of that. So the electrochemistry Bible has Pine images in it. So anyway, but in all seriousness, that is the textbook that will really help you in the fundamentals.
Yeah. I also will mention, and I have links to the Amazons for some of these books. One book I personally like while Barden-Faulkner is considered the Bible of electrochemistry, I find it can be very dense and somewhat difficult to read. But another book is called Laboratory Techniques in Electroanalytical Chemistry.
Who does that one?
That's Pete Kissinger and Bill Heinemann.
That's the one. That's always I can never.
Yeah,
people mention that or whatever. I didn't have experience of that when I was like in grad school or anything like that. But people will usually say it's the Barden-Faulkner or the Heinemann, right? I've heard that so many times, and I just have never. But that Pete Kissinger's great. I mean, that book should be also a good one. That's a good. Thanks for bringing that up.
I think it's just I find it a little bit easy. I think both of them will be very helpful in learning.
Is that one a little bit more like accessible?
I think it's a little bit more accessible, and it's also a bit more. It's like you're doing an electrochemistry experiment. It gives you some hands-on, like this is what the cell looks like. This is where this electrode goes.
That kind of stuff is.
So that's helpful.
The experimental kind of stuff is useful.
Moving on, Prashant Bashit, and we do have a question from we will have, I think, a question from a member soon, so we'll probably address his question sooner. But Prashant is asking, I think this is more of a general question about whether we think, an opinion, whether photoelectrochemical water splitting is really the future for hydrogen generation. Its latest update on market readiness. So truthfully, we don't know, but what we are aware of is that there are lots of electrochemistry companies that are working on these kinds of things. There's a lot of government money that's going into it. There's a lot of research going into it. But personally, I'm always kind of skeptical about these things and whether they're ready for market, whether they can be more efficient than the current method for generating hydrogen, which I think, I don't remember for sure. I think like water gas shift reaction might be the common way that hydrogen's generated, which is
it's the Fischer-Tropsch synthesis, unless that's the other way.
The Fischer-Tropsch synthesis is, I think, carbon dioxide plus hydrogen will give you hydrocarbons.
Or is it carbon monoxide plus hydrogen?
Yeah, carbon monoxide. Right. And then the water gas shift reaction is when you have carbon monoxide and water will generate carbon dioxide and hydrogen. Okay. So I think those are the methods, but
that's not an electrochemical.
Yeah, it's not electrochemical.
I think the problem with some of these things, speaking honestly about it, obviously as an electrochemist, I'd love for electrochemistry to take over the world, but you end up with the trouble of your required electrode surface, a lot of surface area. First of all, you're dealing with processes that are not always particularly high yield compared to something like the water gas shift or some of these petrochemical processes, I guess.
Mhm.
So yeah, the market implementations is it's trickier, it's harder, right? And then you get into photochemical,
Yeah.
like that's even another step in that direction of like problems with yield and problems with efficiency and things like that. It's a wonderful idea, of course, from a perspective of utilization of natural resources, but it is tricky. I mean, even from the perspective of like solar panels, right? I mean, that's a photo electrochemical process. And solar panels, I mean, I have solar panels on my roof, but they are not really economically viable without government incentives. It's just not.
Yeah.
That's just the reality of where we are right now. So, thankfully those exist for those who want solar panels and things like that. But on a wide scale market readiness perspective, much of these technologies are just likely
Infant stages, right?
Yeah, I mean, it in no way should discourage
Yeah.
research of these. Of course, obviously,
Mhm.
these are all worthwhile and worthy research topics. I mean, that's what academia is for, and even industry in some cases, if
Yeah.
there's a technology that could be scaled. But there's a reason why you're not getting hydrogen wide scale from that yet. It isn't in a place for that, at least yet. And perhaps cynically, maybe not ever, or at least for a long time. And maybe that what that means is that it could have implementation on a smaller scale, right? It doesn't mean that you need to get pressurized natural gas or hydrogen supply on a huge scale, but on smaller, individualized sorts of scales, it might be feasible in the future, something like that.
Yeah. There is a question from one of our members, Neil. I think maybe this is right up your alley.
Yeah.
He actually attended one of our your EIS webinar series, and he actually has a question if you can talk a little bit about factors that differentiate potentiostatic EIS with galvanostatic EIS, I think from a practical perspective.
Yeah.
It's not just like, oh, I set the potentiostat and have it go. It's like, is there something a little bit more, I don't know if you have to, if you need some time to think about this question.
Yeah, I'm gonna pull up, I'll pull up a little bit of materials from that webinar if you want to maybe bear with me here. But yeah, Ramachandra, I think that is correct. I did talk about that. That's the 4th week of my EIS webinar series. I talk about the differences between the two. Let me pull it up here.
He also wants to know, can we study kinetics involved in surface electrolyte interface in an electrochemical system using EIS? If yes, please provide me with some projections in regarding to where to start. Kinetics experiments.
Yeah,
So
I don't know that impedance is giving you a tremendous amount on kinetics.
You can get the diffusion coefficient.
Yeah, you're getting diffusional information. I mean, so the kinetics, the speed of the reaction, I got to think, because typically kinetic information is coming from like TAFL analysis and rotating electrodes. You do like Katekielewicz analysis. Those kinds of things give you kinetic information.
Yeah.
I'm not aware of kinetic information being derived from impedance analysis. It doesn't mean that it isn't, but I'm not aware of it very, very well. So I would have to say that I don't know 100%. My hunch tells me that it would be related to like charge transfer resistance, like in some manner of thinking, it makes sense to consider, let's just say the charge transfer resistance, is how favored or not some process is, and that's going to affect its speed. But I don't know, like, is there a direct equation, for example, related to like the resistor value you get from like a Randall's element to lead to like a kinetic rate constant or something like that. The expression, for example, I'm pulling it up now just so I don't misquote it. Like the kinetics, like the kinetic rate constant, where is it here? Was it NFAKC, something like that? Like the kinetic current, for example, that you get from like a Levitch or Katekielewicz analysis. Here, I've got it here. Share. this one. So like, for example, kinetic current, this is from my RRDE webinar. The kinetic current is NFA-Kc. So this is your, electron transfer rate constant. So that's a kinetic kind of a parameter, a kinetic current. All these sorts of things are not, there's no resistance here. Like, so it isn't to say that you can't, but I'm not 100% sure of it. But so I'm not sure of that. But what I will talk about is the galvanostatic and the potentiostatic. Let me just sort of review your question, make sure I'm answering it the way you asked. So the factors that differentiate, expect something like that for galvanostatic. Factors that differentiate between them practically. Yeah, okay. I'll give you a bit of a, and make sure you're seeing the right slides. Is it potentiostat versus galvanostat? So practically, what a lot of times it boils down to is, I'll try to make this more practical rather than like this stuff where there's the math of whatever the impedance is. Practically, low impedance systems, you're going to do galvanostatic. Mid to high, you're going to do potentiostatic. There is this odd phenomenon that I've found that galvanostatic is both more dangerous, but sometimes much better control if you can get away with it. So I almost never say this in a webinar as official advice, and I'm not necessarily giving you official advice right now, but galvanostatic impedance is often a lot better. From the perspective that there's something about the practicality of the control galvanostatically that's a little better. It's just dangerous because like the potential can whip around and then you can have bad results. So I don't often recommend that you would jump to galvanostatic impedance right away, especially if you're doing like aqueous phase stuff, even non-aqueous phase stuff. You probably want to start with potentiostatic. It's just safer because you might inadvertently pick too big of a current and then you're swinging up 500 millivolts, a volt or something. And you do that, you're going to really damage your components. You might irreparably damage your electrodes. And that's going to really cause a bad day in the lab. Practically there's something about galvanostatic impedance. It's more fundamentally like, okay, most of the time with galvanostatic, there's no set point. Like it's just, with potentiostatic, you're picking a potential. Sometimes it's OCP, but it's not always OCP. You might pick 200 millivolts, 500 millivolts, and you're sitting on there and you're doing your impedance. Okay, well, that can, sometimes change the system. Now, of course, it should be steady state. It should be stable and linear and causal, and then that makes it valid impedance. But that's not always the case, right? Sometimes you have stuff happening on your electrode, and that can affect the data. With galvanostatic, it's sort of like, unless you're doing a set current, like you're adding a milliamp and then you're doing a sine wave on top of it, which is rare. Most of the time, galvanostatic, it's just at zero current, and then you add your impedance. That means that it's always at OCP. Like it's necessarily riding on OCP. So what's not implied or understood sometimes about potentiostatic impedance when you do it at OCP is you're not at OCP. You're in potentiostatic mode. The potentiostat cannot do that. It has to measure OCP, which is a passive experiment, and then it has to apply that measured potential. Now, it's just not really possible for any potentiostat to measure OCP, which is like a hands-off experiment. You're not applying anything, you're just measuring with, open circuit, blah, 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 and then apply that exact potential. But if the OCP has shifted ever so slightly, you might be ever so slightly applying a positive or a negative, over potential, something like that. Whereas with galvanostatic impedance, you're modulating the current. And so because you're measuring the potential, you're not at all times, it's sort of implicitly superimposing the signal on top of open circuit, which to me makes it better in a lot of ways in that you guarantee you're like where you want to be. So something like that. I hope that's at least a little clear. It's a little bit of a weird way to think about it. And galvanostatic impedance is not as popular, but I have found instances in working with customers and even personally, where like, oddly enough, galvanostatic just works in a way that potentiostatic doesn't. So it's one of these things. Don't, if you're pretty sure and the literature says to use potentiostatic and you're sort of stuck using potentiostatic and you're trying to troubleshoot the parameters and it's not clean, maybe as you'd like it, my suggestion is to try galvanostatic, but just start really small on your amplitude of current so you don't accidentally destroy something. And there's a decent chance that will be better. And then, really it's kind of like, the general rule of thumb is that like batteries always use galvanostatic. Most other 3 electrode or whatever kinds of systems, you're going to almost always use potentiostatic. That's sort of the practical, kind of thing that I might say. I hope that answers the question in some level of competency here.
Yeah.
There's probably a lot more specifics that could be had about this, but
Yeah.
So
there's a lot of questions. I'm going to run. There's a couple of them that I think are relatively easy to just for quick answers.
Yeah.
But Neil, one question to at least look at and think about is from Shivram Rawat, who's doing a galvanostatic charge-discharge curve for activated carbon. And I haven't really worked with charge-discharge type of experiments and like why, the discharge profile is getting flat or not completely discharged near 0.1 volts at low current density. I don't know enough about that, but there was one question from Hanzo, which is, are there any scripts for Python for plotting cyclic voltammetry polarization scans? We don't know. We just use, Aftermath is the software that we use when it comes to plotting and doing data analysis. That's what we provide, but we don't know any scripts for plotting polarization curves.
Yeah,
and then there was another question just about, I think it was called. There's one question. Oh, can you provide? This is from Syed. Can you provide any guide about an online course which covers content for electroanalytical techniques by Barton Faulkner? The closest thing that I know of or am aware of is there's something called, there's this WISIS, there's a workshop at Case Western Reserve University. They have a 1 week long course on electrochemistry. I actually run one of the instrument sections, but there's an in-person component where it's like 30, there's an in-person component where it's like 1 week, you're there, you're doing labs, you're getting lectures, but they also have it on Zoom as well. So that is an online type of course.
Here's a link,
look at
just so everyone is aware.
Mhm.
This is from last year, I believe. I don't know that the information is updated for 2023 yet, but that link, probably not. It will be hopefully soon. It's usually in August, but that's the link from last year's. I think that you were there in Cleveland, so or at least virtually, either way. But that's the link. That's just some information. It's named after Ernest Jaeger, it's at Case Western Reserve University in Cleveland, Ohio, in the U.S. Anyway, that'll give you a little bit of information about what it was perhaps last year, what it's like, and it's a good one to plug, Alex. Let me sort of, you walked through a question. Let me just back up here. So the galvanostatic charge-discharge curve for activated carbon. So I don't know, Shivam, if you're still watching, if you can clarify, you asked another question about a supercapacitor. So I assume this is related to a supercapacitor, or if it's a battery, I don't know what the application is, but the discharge profile is getting flat and not completely discharged near 0.1 volts. So stop trying to discharge. You're probably ripping electrolyte apart or doing other things. My guess is that you are not doing what you think you're doing, and it's no longer the process you're trying to measure. It will go forever, and you will just continue to be doing a process that you're not concerned. So for example, if with a battery application, if you find that the curve never fully dips at the end like you're hoping it to, that means that there's some SEI thing, there's some electrolyte being ripped apart, possibly the substrate is exposed and it's just ripping electrolyte endlessly. That will never go down, and it will never be an indication. You're going to keep discharging, and it's going to look like you have 5 trillion milliamp hours per gram of capacity, and that's not the case. So you will need to take a look at the construction of your cell. That is no longer the process that you're looking at. I as best I can tell, that would be my advice for you.
Okay. There's another question from Sam. He electrode deposits PEDOT PSS. I can't tell. It's like N32 1 millimeter. I think it's 32.1 millimeter diameter shorter. That seems pretty big, but I don't know for sure. Using CP, I think that's chronopotentiometry. And he's finding that some electrodes are covered with the polymer more so than others. Are there any other ways to enhance and have a more even deposition? I think my comment is just there might just be some trial and error. It could be the applied potential, adjust the applied potential. I think also if you're doing electrode deposition, you can stir, or if you have a rotating disc electrode that you're depositing on, you can adjust the rotation rate. Those kinds of things will also preparing how you prepare the electrode ahead of time will also play a role if you do any kind of pre-treatment to the electrode prior to deposition. So those are all things to create what I would say a more steady, homogeneous system, so that your deposition is a bit more even the time that you deposit. This is just having no experience with PEDOT or PSS or the combination of them for electrode deposition. Those are the things that I might recommend. You may decide to even do potentiostatic mode instead of galvanostatic mode, but those are all, it's just changing the parameters to see whether or not adjusting parameters in your electrochemistry experiment changes the deposition.
I would say to that as well, just a couple of things. The first is that if you're applying X amount of current in a potentiometric, basically galvanostatic kind of deposition over 32 disparate electrodes, there's no guarantee you're going to get N over 32 per channel, which is probably why you're experiencing what you are, right? There's an uneven distribution of current across each of them. And that could be for a number of reasons, like Alex said, that there's a trial and error here. Like, is it an inhomogeneity, or the spatial resolution of some sort of the way of your electrodes in the bath, right, or whatever it is, causing homogeneous deposition. So stirring would probably help alleviate that to some degree, but you'd have to be careful, because if it's like, if there's jagged edges and stirring causes, like, I don't know, poor flow, then one of them might be worse. You could try doing something like decreasing your overall current to try and slow everything down. Maybe it'll go more evenly that way, but also, like, make sure, as silly as it is, like the electrical connections are proper, because like current is like water, it's going to follow the path of least resistance at all times. So in theory, you have a 32 like spider arm pathway of 32 paths for your current to go from your instrument, but that only is going to be split exactly evenly among all 32 if you have the same amount of resistance in each pathway. And if you don't, then it won't. So slowing things down, stirring some of those, you might have to have some trial and error, but frankly, I'm not surprised, because it's going to be almost impossible to have 32 perfectly identical surface condition, resistance of path, all of that, 32 exactly identical electrodes. The best you can hope is that you have a roughly similar amount of deposition on all of them, would be my guess. So yeah. Sorry, I don't know if you had another question. There's the one after that was from Mat Byung, says, performing CV for activated carbon. Why do I see bubbles on the CPUT electrode? I'm not sure what. Even though I applied the voltage window from -0.9 to 0.9 for KOH.
On the counter, wait, this is
CPU, I just don't know what CPU and then TEE. I don't
wait,
know
on
exactly.
this is Matt Beyond's, hello, I was performing CB for my activated carbon electrode. Why do I see bubbles on my counter electrode? Even
Is
though
that supposed to say counter? I'm not sure, it might be a typo.
Oh, maybe.
It says CPU space TEE electrode. Am I reading that right? It
Oh,
just looks like maybe that's a typo.
well, I'm just.
Oh, the question's repeated down. I see. Okay. Yeah.
Okay.
The question was twice, and the
Okay.
up top there was okay, I'm sorry. Here we go. Okay. So oh yeah. Okay. So you see bubbles on your counter electrode, and then well,
so
yeah, go ahead.
yeah, I mean the potential that's applied on your counter electrode is going to be different than that applied on your glassy carbon working electrode.
Unless you have a 2-electrode system.
Yeah, unless you have a 2-electrode.
I assume you have a reference electrode.
Yeah.
And if that's the case, then you have no idea whether the voltage at your counter electrode has anything to do with -0.9 to positive 0.9.
Correct.
Could be absolutely anything.
Yeah.
And then also consider that you're in KOH. So as the pH goes up, the potential window goes down, which means that your positive window of 0.9 is probably very high for alkaline.
Yeah.
So it's possible that at the extreme there, you may be having a really aggressive electrochemical environment going on, and it could be producing bubbles on your counter electrode.
Yeah. So Ramachandra has a follow-up question about CV plots, and what it looks like. I'll just share my screen, and maybe he can comment, but basically it sounds like, and if I just get, this takes me a little bit of time to make sure the line thickness is good, but maybe I need a little more, like the quote trustworthiness. It sounds like he's getting some voltammograms where this is voltage and this is current, where some look like boxes that are kind of like this, but then sometimes he's getting voltammograms that look like the traditional duck, or it looks something like this. And he's just wondering, how is it's like, this is what I expect, but this is what I sometimes get. And maybe the question is why. And without seeing it exactly, without seeing the data exactly, we can only comment. But trustworthiness of data, I would say, comes from two things. One, one thing is, I would always pick a system that is kind of reproducible. So how do you build trust in electrochemistry? Do you have...
I just don't trust it. That's
we just don't trust it. So I would say reproduce a well-characterized system that was published in the literature. Something like ruthenium hexamine or ferrocene for non-aqueous systems. If you can reproduce what was done in the literature, then you'll absolutely, then it's like, okay, I trust it. The instrument is performing well and the data is performing well. The other thing to look at and think about is, does this make sense? And what are my parameters, right? Sometimes you'll get these differences. You'll get differences in the voltammetry because of a setting. Like this might actually just be a change in the scan rate, scan rate difference. And because this looks like double layer charging, but this looks more like, a regular duck-shaped voltammogram. So that's kind of my take a little bit, but that's how you would build trustworthiness, is by being able to reproduce a system that's been published, that you can do it multiple times, and then you can say, okay, I trust this data. So that's my take on it very quickly. Hope this was helpful. Okay, let's
look through. There was some that we might have.
Yeah, I'm also trying to, because we answered got Galvanostatic PEDOT.
Yeah.
And some of these questions are also a little bit we could go back to Stu's question. Oh, let's see.
Well, there was one that can you explain how the current becomes negative during backwards run in the CV?
Yeah.
Well, that, I mean, the simplest answer to that, if you want to share, you can, but I mean, basically that.
Yeah, I can share.
I mean, when you scan negatively, you're doing a cathodic process, and negative current is just describing the direction. So there's really no such thing as negative current in the perspective of like, like it's just a direction. So
Yeah.
it's arbitrary is the point.
Yeah, but yeah, so sometimes one thing that's very confusing to people is like, oh, this is like +1, and this is like plus 0, 0.5, 0.5. And why do I have a negative current at a positive potential, right? Why do I have that? And it's because you should think about current as the flow of ions. And this reverse wave is the result of having molecules. So when you first do this sweep and you get this, the concentration profile next to the electrode is that of the oxidized molecule, right? It's the oxidized molecule. So now I have all these oxidized molecules near the surface of the electrode. But when I get to this point, right? When I get to this point and I have this negative current, the potential is low, or it's smaller than the potential required to maintain this. So thermodynamically, electrons will move from the electrode to the molecule, and that represents a negative current. So even though the potential is positive, the current will be negative. You can do another experiment like this. You can actually just hold the potential, watch the current, and then add some redox couple to it, and you'll just see like, oh, the current is changing, even though the potential is just one value or another. So it's based on the redox processes and species. You should think about electrochemistry as there's the electrode, and then there's the molecules and stuff in solution. And there's electrons that move back and forth, and this has its own potential. Like, and we can talk about this too, because Stu had this question, but this is related to the Nernst equation. The whole thing is related to the Nernst equation. So if it's thermodynamically the case that these want to donate an electron or get oxidized or get reduced, they'll do it at a potential where it's thermodynamically possible. So that's hopefully that just answers that. Hopefully answers that part of the question. Okay.
Does Warburg tail length indicate diffusion into the electrodes for solid state batteries? Mike asks. Tail length. So maybe.
Maybe.
I'm trying to think. So let me share.
Because the tail length is somewhat dependent on.
It's related to the Warburg coefficient. Well, it's right. Well, it's frequency dependent, but the point is that the tail length is related to the Warburg constant. So Mike, I'm going to think through this with you. So we're gonna go on an adventure together. So this data is not. I want this one. I want the 0 1. That's Warburg short. You're thinking about Warburg infinite, basically, something like this. Does it curl down? I just want to find a data set that's hopefully reasonable. Yeah, that's not what I want. I want something that's more like Warburg. All right, so let's say, for example, I've got all out of Warburg for you. Let me just. Do I have one already built? Warburg infinite. That's what I want. Good thing I've already drawn it. All right. So let me just do a quick thing here, and I'll just sort of talk this through why I think that the answer is maybe. Get rid of some of the high frequency stuff. This isn't going to fit perfectly. This isn't. It's not really the point, so I'm not too concerned about it, to be honest. Just want to try to answer your question. And the other thing is that this is not solid state, so so bear with me here. Where am I at here? I gotta kind of play with this a little bit. Increase this range. I'm just going to get a okay fit for a second, and then I'll talk through this with you. Just give me a moment, I promise. Let's see. Ugh, I'm doing that. Is this even the right model? I don't know. I'm trying to get this quick for you, and it's not super quick, so my apologies. I'll get this somewhere halfway decent. Oh yeah, I gotta fix up some of these results. Around 10 or 11, something like that. Get this somewhere here. And then
I don't know if now is also a okay time to talk about this. Because we're talking about Warburg elements, Race Bannon is asking a question to describe the difference between all three types of Warburg elements.
Yeah,
maybe that, I don't know if that's, I'm assuming he's talking.
Oh, yeah, that's a little better.
Yeah, I'm assuming he's referring to like short, infinite, open, and all the variations between.
This thing's being stubborn. I got it though. Yes,
you got it.
Yes, I can answer that question in just a minute. Yeah, thank you for letting me.
Yeah. I
I'm
just
sort of
figured maybe it
focused.
was
You're
on the
watching me.
same.
You're watching me stumble my way through an annoying circuit fit live. But I got it. It's fine. All right. The point that I'm trying to make here. Okay, so the Warburg tail indicate diffusion into the electrodes. So if you're saying, let me put it this way. If your question is, does a long tail mean it's diffusing in compared to like a short tail means that it like isn't diffusing in, that's tricky. I don't know if that's exactly the kind of answer I can give, but what I can say is that, for example, like in this, this data here, here's my tail, right? And my Warburg constant is 2000, whatever. As I increase the W, the tail grows. I'll just zoom out so you can see it, right? So like as the W increases, that tail just goes longer. It's going to extend out. And as the tail gets smaller, it goes down. Now, the Warburg, I think I have it here. Let me pull it up. The Warburg coefficient, this one right here. The Warburg coefficient is proportionate to the diffusion coefficient. So probably there's an answer to your question in terms of like, does a large or small diffusion coefficient provide insight as to the level of penetration perhaps that you might have in your electrodes of your battery? Now, the tricky thing here is that you're talking about solid state batteries. So I don't know if what I'm saying is appropriate from the perspective like diffusion coefficient. This is typically liquid phase. So I don't know if this is appropriate, and it may not be. So my apologies if that's the case. However, what I'm just trying to illustrate to you is that the tail of the Warburg is proportionate directly to the W, the constant that itself. And that is related, as you can see here, basically inversely, essentially, to the diffusion coefficient. And so there might be a connection that you can draw therein, whereby the length leads changes in W, which leads to changes in D, and that could be an indication of something related to how the diffusion's occurring in or around. Now, that was also assuming infinite Warburg, and maybe you're actually talking more about something like this, which is be a Warburg short. So that's also a possibility. But that's the best answer I can kind of give you on that. And other than that, the other reason why I wouldn't comment further is because I'm not an expert on solid state systems, to be honest. Even batteries, I've done a lot of work on, but those still have a little bit of electrolyte and they would be not considered solid state batteries to the best of my knowledge. Warburg here. So someone, what was it? You said that someone who explained the difference between all three types of Warburg. Yeah, I have a whole webinar on this. I will go through it as quickly as I can, I suppose. The other answer to that, which is less satisfying in the moment, is that we have the videos from those webinars in it's in our, right, if you're a member, if you become a member to our YouTube channel here, you can watch the full webinar recording where I talk about this, but I'll show you very briefly.
I think we also have, I don't know if it goes over, like he talks about and I'm not as familiar about Warburg related stuff, but we do have a video, kind of a snippet that is, if I can find, let me just see if I can find the link.
Yeah, you find out. I'll just talk through this really quickly. So there's the three kinds of Warburg generally are infinite, open, and short. So infinite and then finite, and there's two kinds of finite. So I'm going to move forward with the assumption that those are what you mean by the three. You might and perhaps have a different idea, but that's what I'm understanding is the three. So it's basically two, and then one of the two has another two. So infinite basically means what it sounds like. The diffusion plane is infinite, or at least semi-infinite, which means that the distance that molecule is traveling to get to the electrode is infinite compared to the size of the electrode. Okay. It basically means the diffusion layer thickness, which is sometimes used delta to refer to the, is infinite, semi-infinite. Okay. It's, it's somewhat indistinguishable from the bulk. You can think of it that way. And so the result of that is you get this big tail, which is what I just talked about with respect to Mike's question about the length of that tail is proportionate to the constant of the W. The finite kinds of Warburg, short and open, refer to a situation where that diffusion layer thickness is no longer infinite, it is fixed. It is a finite number, but it is not infinity. And so finite short refers to the situation where the diffusion occurs through that fixed length and the boundary is absorbing. That's another word for it. The finite open is when you have a blocked boundary. This one, I always have a hard time using the right words to describe this. And to be honest, I have a hard time like describing it and rationalizing it in comparison with things like constant phase elements and capacitors, because they seem, even to me, kind of indistinguishable, like from a phenomenon perspective. But effectively, it's that there's a diffusion layer thickness, but it's it's not absorbing the diffusion, it's reflecting it. So it's really a boundary for engine. For those who have had engineering training, boundary conditions is one of the main things you do with all sorts of partial differential equations. So it's just a difference in boundary conditions. One of them absorbs the diffusion through a set thickness and one of them reflects it, but there's still a set thickness. How that is different from a capacitor is, in my opinion, somewhat nebulous, but for what it's worth, that's the super fast explanation of the three kinds of Warburgs that I can give you here. I think there was another question from Ramachandra. Is that right?
Yeah. So he's asking, what are the methods that help me study surface kinetics in electrochemical systems, liquid solid junction, three electrode systems? He's interested in references, articles, methods, and also does higher and lower RCT values in an electrochemical system, the Nyquist plot, speak about the sensitivity of the working electrode in sensing species in the electrolyte? And then lastly, I think this is just a continuation in the three electrode system when using EIS. I want to say, at least for the second part of the question, higher or lower RCT values, at least for a three electrode system, are somewhat a function of the potential. So if you have a redox species in your solution, you'll have lower RCT values. And actually, there was a question earlier about this as well. So hopefully I'm also addressing this. But when you have a redox molecule in solution, the potential where that redox molecule is actually able to undergo an oxidation reduction reaction, it lowers, the EIS indicates that the RCT, the charge transfer resistance, is lower. And that's because electrons are transferring. It's a kind of interesting and weird way to think about it, because electrochemical systems are just weird. In what situation does the resistance change based on the applied potential? But that's exactly what some of these electrochemical systems are. So to answer your question about does the sensitivity of the working electrode, like does a high RCT affect the sensitivity of the working electrode in sensing the electrolyte? I want to say no, because it's a function of the potential.
That's exactly the right answer. Yeah.
Yeah.
I was going to say it's like what you're asking about is like the downstream effect of the thing that actually affects that, right?
Yeah.
The potential is what affects its ability to do that. And by changing the potential, you will end up with a change in RCT, but it's not the RCT itself that's affecting the sensitivity. It's the potential that's affecting it. Yeah.
Yeah.
That's the right way to think about it.
And when it comes to methods for looking at like surface kinetics, people are looking at like cyclic voltammetry,
RDE.
Huh?
RDE.
RDE. RDE, I think, is, at least for me, like conceptually one of the easier ones, because you're able to, and Ramachandra, you're a tier 2 member, so thank you. There is in the archive of webinars, Neil had created an RDE webinar. And in that RDE webinar, there's 2 parts. He goes over looking at the kinetic current that you get in a rotating disc electrode, which gives you what I would consider to be very direct surface kinetics information. So that is something that you have as a tier 2 member. So I would encourage you to take a look at that, like as a complete bit of information. Other articles, another book that might be helpful, which I know we talked about different books, but there is a book by Savant, who is a dead French electrochemist. Most chemists have who are famous have died, whose books and equations who we all reference. But he has a book on like molecular electrocatalysis, and it's definitely a good book when it comes to understanding kinetics and electrocatalysis. So that's another resource I would recommend. Jean-Michel Savant is a person who does that.
Srijib, the MSR cable doesn't make the control cable does not make it more precise. It just does it automatically. So you can absolutely do Kotecky-Levitch and RRDE analysis manually. So you just have to change the knob on the rotator to be 900 RPM.
Yeah.
Click go on your experiment, and then change it, click go again. All that cable is going to do is allow you in Aftermath, for example, to do something like this. I'll show you.
It might be a little bit easier to use the cable, because if it's a very sensitive knob.
Yeah.
Like you touch it, you blow on it and it moves.
Yeah.
But basically that's Neil's right. It won't make the calculation for the Kotecky-Levitch plot different. But for having issues getting it to like 900 RPM exactly, the cable will be a little bit more helpful.
So you could do something like Levitch, like we have it just allows you to do stuff like this. Like we have a Kotecky-Levitch or Levitch RDE. So you can do like, here's your sweep limits, whatever sweep rate, and you can do initial speed like 400 to 2500 and however many. You can space it out. Levitch is the most common. That's just by the square root of the rotation rate. Kotecky-Levitch is by 1 over the square root of the rotation rate. And it's just, so this would, if you do it this way and you pick the number of iterations, it'll do 4, 9, 16, 25, whatever the in this case 3600. So it's going to space it out by the square root of the rotation rate. Or you can just do a single one. Where is it? Rotator methods, RRDE or RDE. I guess it depends if you're doing ring disc or just, I'll just pick the simplest one. So in this case, it's like, this just allows you to set the rotation rate here for your experiment, rather than having to change the knob with your hand. But it's not necessarily more precise. There's gonna be it's not going to affect the results of your Katekielewicz analysis or your Katekielewicz plot appreciably whether the rotation rate was set here or with the cable. It's more of a convenience thing. That's what I would tell you. I see that you're asking if Stu is still here. We'll wait and see if perhaps he
and
is back to hear about the nurse. There was one other question. I just went by. I wanted to make sure I didn't miss anything.
Yeah. There's a lot of questions, and we've kind of been jumping back and forth a little bit. I remember Vinod asked about charge transfer resistance decreasing with increasing potential and wanted to know why. We did talk about that earlier with Ramachandra's question. So hopefully that addresses your question, Vinod. But if you need a little bit of more clarification, let us know. We can talk a little bit more about it.
The voltage difference between the anodic peak and the cathodic peak.
Oh, it's significance. So that's a Nernst equation thing. So I can wrap
then
up
you're
ton
gonna
of stuff.
then you have a reason to do it whether Stu is gonna if he's perhaps still watching.
You can talk. I'm gonna just try to share
no worries.
screen
There was one thing. Let me get the camera on you here. Hang on. Okay. Sorry, there was one thing, and I'm gonna find it.
Yeah. Oh,
trying to make sure we get through these questions here, right?
Yeah.
Charge transfer resistance is decreasing. That one I already got.
We can't like mark these or anything.
I know. It's just looking through the chat, just doing the best we can to get through everything here. Longer lead. Oh, this is what I saw. Sam had said maybe longer lead lines have higher initial impedance and lower yield on some electrodes. So that may be the case.
I'll stop sharing if you want to.
No, it's fine. You can keep sharing.
Okay.
Yeah, right. I know it's not seeing my face as I talk, but it's okay. Fine. Yeah, your face is better than mine anyway. It's fine. You can go ahead and share again if you want. This is a quick thing. I just wanted to say that when you have long leads, that is going to eat away at your it's going to add impedance basically to your system. So you'll have higher impedance, can mess up impedance measurements in particular, and it's not changing the fundamentals of the electrochemistry, but what it is possibly doing is changing like how much loss there is. It's like the IR drop. That's a problem. So generally speaking, the advice that I have is to shorten the lead lines, shorten the number of connections between your potentiostat and your electrode, if at all possible. Tighten everything up. Don't have a million different cables connected to all sorts of stuff. You want to try and limit those types of things if you can, because it practically is probably lowering the yield, but what it doesn't necessarily mean is that your electrode is bad. Is the way I would say that.
So when it comes to the Nernst equation, this is something I learned from Dan Shearson, who's at Case Western, who will do this experiment or talk to you about it if you decide to take his class. So let's say you had a platinum wire. So let's say you had a platinum. Actually, let me back up. This is the Nernst equation. This guy here. It says that the potential, whatever your system is equal to the standard potential minus RT over NF. So all this effectively are constants at room temperature. The gas constant, temperature, number of electrons transferred, and then Faraday's constant times ln of Q. Q is really actually that's more of the ratio of it's more of
the term reaction quotient. Is that right?
Oops, yeah, reaction quotient. I just looked at from so it's really more of the natural log of, I think it's the oxidized species, so concentration of like
reduced over oxide. I don't know.
I never remember this.
It's one or the other.
It's one or the other.
In fact, there's a name for the other way, and we had it on a previous live stream, right? Someone put, that's going to drive me nuts. What's the name? 1 over Q. There's a name for that. Somebody type it if you.
Right.
What's the name for that?
Binding constant.
Is that binding constant?
Yeah. That guy was talking about the binding.
So
constant.
Q is like a dissociation constant in the context of this.
Yeah.
Anyway, sorry, I'm just derailing you.
No.
It made me think of it.
No, this is fine. But basically, it's a relationship between like just the oxidized and reduced form of a molecule. So if you have like a plus electron equals B, or is in equilibrium with B, it's like these are the concentrations of like A and B here. So this is an interesting thing. So it just tells you that, what I find to be interesting is that the potential really at the end of the day is governed by the concentration, the ratio of the concentration of these species. So one question, if you ever take Dan Shearson's course, is that if you have a platinum wire in solution just by itself, not connected to a potentiostat, not connected to anything, the energy level, the potential of that platinum wire will be based on the concentration of A and B in your solution. That the Nernst equation basically pegs the potential of your system to what's going on here. So a lot of times in general chemistry, you're always thinking about, oh, what's the potential going to be depending on this, or what we typically do in electrochemistry, if you're doing a cyclic voltammetry experiment, is you're using the platinum wire to change the potential, which is thus changing the ratio of the concentration of these species. But the opposite happens too. You can change the potential by changing the ratio of the concentration of these species. And so when you're doing like redox flow batteries, which is the case of Stu, you're able to change the potential by adjusting the ratio of these two concentrations. So that is that's the important thing. And then when it comes to doing and this is related to when you're doing a cyclic voltammetry experiment and you want to know why there is a difference between these peak potentials, right? And that difference typically is like 59 millivolts, right? Or 60 or 57. It's around there.
59 is
59, I think, is the number.
Mathematically, it works out something like that.
So that number, right? Because I think Matt was asking about this difference, and it's 100% just due to the Nernst equation. Like when you actually plug in all of these, right somewhere in the middle here, you have it where these two concentrations are equal to each other. And so you get like 1, 0, and the E naught is when the concentration of these two are equal to one another, right? So somewhere in the middle here, you have E naught. And this difference is really just a manifestation of the Nernst equation. When you convert the natural log to like log base 10, there's a constant that comes out. And when you just multiply these numbers by it, you get like 59 or something along those lines, or 2.89 something. And hence you get this difference of 59 between the anodic and cathodic waves. And to address a little bit more about like, well, what does it mean when, this difference, because you can actually get a difference between these that is, that's different depending on the kinetics of your experiment, right? So if you're oxidizing something, you may actually see in another voltammogram that, there's actually, it's a lot farther apart, these two waves. And that has to do with the kinetics of the electron transfer. It means it's a whole lot easier to go one way. That's like the alpha of your system. It's a whole lot easier to go from A to B than it is from B to A. It's a slower process. So the distance between your anodic and cathodic waves has to do with kinetics. It also may have to do with coupled chemical reactions. It also has to do with things like IR compensation and solution resistance. There are a lot of things that can affect it. So I'm hopefully that helps you understand a little bit about the difference between the anodic and cathodic waves in the CV. Just trying to get through as many of these questions as we can, and I think
there
we
was
get
a couple
more
here. Yeah, we'll go as long as there are questions or we get laryngitis.
Yeah.
So there was one that I wanted to just comment on here. Oh yeah, let's see. Sorry, Prey asked, have you talked about using EIS with distribution of relaxation times analysis, for example, if you wanted to separate fuel cell processes with very similar time constants? So I have talked about it, and no, I haven't done it because I don't know enough about it, and or we don't have, so I'm actually, yeah, this is part of it, is I don't know if it's like, if it's more of a hardware thing or a software thing. I know of it and I have not done it. That's the best I can tell you. I know that distribution of relaxation times is supposedly one of the only ways that you can really differentiate processes where you have similar time constants. And I just, it's not something that I have experience doing. In those cases, I don't have a lot to share, all other than that I know it's a thing and I hope that it works. So apologies for not having more information about that. All I do is that I know that it's a thing.
So question, have you heard of LEIS? I'm just looking at other questions.
LEIS.
Yeah, J1 Bay is saying LEIS
I've seen
area
that.
maps.
What is the L?
I don't know what that stands for.
Is it linear? Localized electrochemical impedance spectroscopy? Oh, localized. Okay. So that's
Localized?
probably just
Oh,
that's a
okay.
physical setup thing. I
Okay.
want before that though, I
But
wanted
yeah.
to, there was one Ramesh asked, can we find the electrochemical surface area using 3 electrode setup? I wanted to show you how to do that. Let me just get like a blank sort of workspace here. I'll kind of show you. We're using the whiteboard, or we're using like a
I
PowerPoint slide or
I went to PowerPoint and used
you
to
just-
annotate.
yeah, that's better.
That's
I'll do the same.
That's what I was using.
Yeah, the whiteboard thing was weird. We tried that. It was like it wasn't as easy.
It wasn't as easy.
Yeah, we're using Zoom and it has a
Yeah.
whiteboard thing, and Alex and I were trying it like weeks ago, and it was like,
Yes.
I don't like the whiteboard thing. It's weird.
Yeah, once we had annotate, it was
Yeah, annotate was
much
a little better.
better.
This is like insider baseball going on right now.
Yeah.
That's how we're preparing. All right, annotate. Yeah, let me show you one specific example about getting the electrochemically active surface area.
Oh yeah.
So for example, the easiest or most popular, I should say, example is with platinum. So when you do a CV on platinum, many of you are probably aware of this shape here. I'm going to test my artistic skills here. Okay. So this is something like what you get when you do platinum CV. I really should have drawn this section bigger. Anyway, let's say you have a platinum. This is a platinum electrode. So you have a disc and a shroud. I'm going to make the color. I don't have like silver. That stinks. All right, this is platinum. There you go. Brown. Platinum's brown now. So here's my platinum disc. So the surface, like this is a 5 millimeter OD disc. So that, or maybe you have a platinum on carbon film on your glassy carbon, whatever. So the point is you have some known geometric surface area. Well, what people do to get the electrochemically active surface area is they do a simple CV in sulfuric acid. And what you do is that the platinum CV is very interesting because there's all these features. This right here is platinum hydrogen desorption. This down here is platinum hydrogen adsorption. This is basically like platinum oxide reduction or oxygen reduction if there's oxygen, but usually you're doing this in like neutral-ish, whatever. So this is just oxides on the platinum. This is the platinum oxide formation, or sometimes hydroxides or something. There's variations in what these are called, but basically something like this. What is done is really pretty simple, actually. So the only place in the platinum CV where basically nothing, for lack of a better terminology, is happening is right here. I should have drawn this I should have drawn more distance here. I just drew you know what I mean? I hope you know what I mean. Anyway, the point is basically in this region, whatever potential this happens to be, this is basically just double layer capacitance. It's like one of the only places in the platinum CV where like the positive and reverse scans, there's nothing going on but double layer. So what it allows you to do is subtract this capacitance, this current, because it's just double layer capacitance. And so what you're left with is that technically or at least, well, I don't know, theoretically, technically, whatever you want to say, the surface area here of this current data, okay, is related just to the platinum hydrogen adsorption desorption process. So what you can do is you can integrate it, you get the surface area. And what you do is you relate it to the theoretical ideal. Okay, and the theoretical ideal is 210 millicoulombs per centimeter squared. Is that right? So I think that's right.
So
okay, so coulombs is what you get when you integrate current, right? Current is in amps, which is coulombs per second. So when you integrate current, that's supposed to be an I dt, you get charge, right? Which is in coulombs. Okay, so basically you're integrating this, you're getting the surface area. This would be this is a CV, so this is voltage, but pretend this is time. Okay, so you're integrating this, you get a charge, and you divide by the surface area. And you're comparing it with the theoretical charge for this process. And so in doing so, you divide, so that the operation would be, you integrate this and you get coulombs, and so you divide that many coulombs, or this might be micro coulombs. I might be screwing this up. I'm sorry about the unit. Please fact check me and find the right unit. It might be micro coulombs. I think I might be off. Anyway, the point is you divide the amount of coulombs you get when you integrate this by 210, and then you get coulombs divided by coulombs per centimeter squared, right? So coulombs cancel, and you get this number you get when you do that operation is your ECSA. It's your electrochemical active surface area. So that's roughly speaking the procedure. For platinum, okay, there are likely analogous procedures for other materials, but that's the one for platinum that people use commonly for ORR before they do RR. You're trying to figure out I have whatever, this many grams of platinum or platinum on carbon or whatever it is, but I want to get my ECSA because that might be the thing you normalize to later. So that is hopefully a crash course quickly on how, and again, please I think it is micro coulombs. I think I screwed that up. So please make sure you get the right numbers, but that's roughly how it's done. What was the LEIS? Oh, there's one here too about when resistance is very low, we generally do Galvanostatic EIS. Yeah, that's right. But as we change current value, EIS graph change, how could I select good EIS curve? Yeah, so you want to get, if the impedance is now, okay, here's the tricky thing, right? Impedance is really hard to get consistency in general. It just is. So I'm not surprised, unfortunately, that changing parameters makes it change. But in theory, you want to be in a place where changing the amplitude of your applied signal does not change the result. That's where you're in the good spot. So, let's say in theory, you have this current and this impedance response, and you increase the current and the impedance response changes, and you increase it and it changes. Well, in theory, maybe if you keep decreasing, if you decrease it, the impedance doesn't change. You decrease it, the impedance doesn't change. You want to probably choose the highest current in that range where it doesn't change. If it's always changing, you might have something else wrong. You might have some instability in general going on, or your current, your results are not stable as much as you think they are because your current perturbation is too large. Run Kramer's Kronig on your results always and see that they're that it's good adherence. That might be helpful. But ideally you want to be in a towards the top end of your amplitude where it did not change appreciably when you change the current amplitude or potential, if you're doing potentiostatic for that matter. That would be my suggestion. So there was an LEIS one here.
Yeah.
Area maps. Do you normalize the area by scan area or sample surface area exposed to the electrolyte? Well, I would guess if you're doing localized, then you're not going to do it to the whole electrolyte area because, which I don't have experience with this like practically. I haven't done. I mean, I assume it's some sort of like a local probe that, you know, does impedance only with respect to a small. Somehow it's isolating one part of the surface area of an electrode or something like that, and so your impedance response is like. I see you responded. Little research. I'll get to that in a second. You know, you can like put a probe in one spot and like the impedance response with respect to just that. It doesn't make a lot of sense to normalize to area that was not involved in the response itself, because electrochemistry is such a sensitive surface science. You want to normalize to the area that was involved in just those results. So my suggestion would be to normalize by the scan area for what it's worth that you put, not the whole sample surface area. That doesn't make sense to me, but I could be wrong because I don't know exactly the application you're referring to. So I that may not be perfectly accurate, I guess. Sorry, you said that you changed it from 5 milliamps to 20 milliamps and you always find it changing. So probably you don't want to go any higher than that. I would start going back down. I would go from 5 milliamps and drop it progressively.
That's the amplitude, right?
I assume that's the amplitude. Yeah, I'm assuming. I would go down further. You know, eventually, if you go too small of an amplitude, you might find you don't get any results, and that's fine. Then you're reaching the lower limit, but don't keep increasing it if it keeps changing, because you might be actually getting dangerously high. That would be not potentially helpful. You might damage something in your system. It's possible.
I can answer the next question quickly. Neither of us are Russian, Henry.
No, that is, yeah.
So
application is corrosion.
Yeah. Also, Race Bannon has, is there a 1-to-1 ratio between cyclic voltammetry and galvanostatic charge-discharge? Thanks. So
1-to-1 ratio. What is this?
Yeah, it's Race Bannon has a question. I guess I just like when I think about cyclic voltammetry. Well, I don't know what it's like the ratio between cyclic voltammetry and galvanostatic charge-discharge, or like data within. Perhaps we need more.
I'm not sure I understand. Ratio of what? I guess that's the question. Yeah, I'm not sure I understand. Yeah. Physics Insight asked before that, what are the critical problems in batteries and supercaps that need to be addressed and that can really bring something new in the field of electrochemistry? So, I mean, I can ramble about this for a little bit, but with batteries, you know, one of the things that's really becoming more and more evident as time is going on is that I don't know how to put this more elegantly. Regular technology is getting better faster than battery technology. Like we all have these, right? We've all got our smartphones. Like 90% of the weight of your phone is the battery. It's almost all battery. Almost all of the volume, the density, all of it's the battery. The technology is better, and the battery is the thing that's holding it back to a large degree. We are, you know, and have improved lithium-ion battery, which are the main, you know, chemistry that's used to power consumer electronics as well as electric cars. Increasing and improving that technology rapidly, but not faster than the rate at which the demand requires. And so, you know, the critical problems in particular, you know, some of the obvious ones are with respect to electric cars is that you are to which, not to say there isn't penetration, you know, here in the US, we have Tesla, we have, you know, even a lot of the major brands have electric versions of electric vehicles. A lot of them do. But, you know, to the best of my knowledge, something like at most 1 to 3% of total vehicles are electric globally. Maybe it depends on the country. Some countries might be higher or lower, right? But it's not, you know, overtaking, you know, hydrocarbon or petrol or whatever, diesel, all that kinds of engines yet, or really anytime soon, probably. despite the, desires to do so, I would say. And part of that reason is a lot of the norms with which we currently operate globally. And that's, to a large degree, refueling is a process that takes, anywhere from 3 to 5 minutes. So when you think about, I'm going to throw out some things in battery terms, so you may not totally understand this, but C rate is the rate at which you charge something. So 1 C takes an hour, 2 C takes 30 minutes. So you're talking about needing to charge 10 to 15 C. There's really no good way to do that without destroying your battery very fast. So one of the challenges, to directly answer your question with respect to batteries, I can't speak as much to supercapacitors. I don't have a lot of firsthand knowledge of supercapacitors. I'm sure there are challenges, but supercapacitors are already, or at least capacitors, are used in cars and for quickly, discharging a lot of the electronics and things like that. A lot of the challenges are being able to charge up a battery for your vehicle with around the same level of rapidity that you can fill it up with petrol or gasoline, right? Whatever country you're in. And that's difficult because batteries very quickly degrade their efficiency and capacity when they are charged and discharged very quickly. When you can charge and discharge them slowly, they last longer, but nobody has an hour to fill up their gas tank or fill up their car's battery, right? So that's the tricky thing. And then, the other part is just the simple increase, the problem with everything, right? When it comes to fuel cells, when it comes to batteries, how do you increase power density, while decreasing material usage, decreasing cost, and improving, accessibility or availability of products, right? So all of those are like real difficult challenges that don't have easy answers, and there's incremental improvements that simply do not yet reach the level with which we are improving electronics or accelerating the need for those kinds of development. So it's tricky, it's hard. I think we've come a long way since John Goodenough in the 80s developed the lithium cobalt oxide cathode and jump-started the lithium-ion battery technology for sure. And then a Japanese electrochemist, I'm forgetting the name, I think developed carbon graphite as the state-of-the-art for the anode, to give credit where it's due. But it's a process. It really is.
Yeah. Just following up on playing with my headset.
Yeah, was it buzzing for you?
Yeah, it buzzed. I felt like maybe I just like
I think there's a
pulled it
static thing going on down there.
Oh, okay.
It was buzzing on mine earlier a little bit. Like I was testing the wire. Anyway, I think it's us.
It's us.
Okay. There's some static thing. We're in this room. It's just carpet.
Yeah.
Carpet gives static. It's a pain.
Yeah. So Raceban he meant like once he gets the results of galvanostatic charge-discharge, could we use those results to plot cyclic voltammetry? I think that your intuition is correct, that you cannot use data from a galvanostatic charge-discharge to determine or get a cyclic voltammogram. I mean, maybe you could get some general intuition about potential ranges, but it's not like you can use one to get the other. They're different techniques.
It's not going to work. Yeah. Much of the assumptions and the premises behind which a cyclic voltammetry experiment is based aren't going to work by plotting it with those data.
Let's see. I think you talked a lot about batteries. Stuff behind Henri is asking about what do we think about battery and super condensator, using battery for total charge and saving recuperation energy in super condensator, and also make the roof of Tesla from solar panels.
I'm not sure what a super condensator is.
Yeah, me too.
I'm guessing that has something to do with using water or water vapor. If it's a condensation sort of a process, usually those kinds of things are using and taking advantage of the enthalpic the energy that you can get from having water change states, basically. So the first thing that I would say is that if you have anything like that, that just requires onboard storage in your vehicle of liquid or water or gas or something. I mean, any more storage or whatever is going to increase the weight of your vehicle. It's going to increase, needs of more hardware needs and things like that. So just from that perspective, you're running into problems. And so, the other part of that is making the roof of Tesla from a solar panel. I guess I have two thoughts about that. The first is that that's probably just not going to work. First of all, the surface area of the Tesla is not of a car isn't enough to facilitate the kind of power that would be anything related to useful. Secondly, solar panels, as I said before, is that solar panels in and of themselves are not very cost effective as it relates to anything without governmental assistance. At least here in the U.S. in particular, and I think in most places, I believe that's the case. It's just an efficiency thing, and then availability of materials and recycling of or the disposal of them afterwards is a big problem that has not been solved. It's not so cut and dry, like, oh, just throw solar panels everywhere, our problems will be solved. It's not that simple. And then the other answer I have to that is, I don't mean this, I'm not trying to be mean, but if that were something that would help, I would guess they'd probably have done it already. Right. I mean, it's like, whatever you think of Elon Musk, he is an engineer with a track record of accomplishing some pretty incredible things, including sending rockets to his car to outer space for no apparent reason. So if putting solar panels on the roof of a car was both cost effective and helped with the energy needs of a Tesla, they would probably be there by now. So that's what I would think about that for the most part. Supercapacitor, which range of value, ampergram current. It's better for GCD's cyclic stability performance measurement.
I was gonna.
Sorry, did you have another? Yeah.
I was gonna answer. Well, first I was gonna say, Race, thank you for becoming a tier 2 member. We really
much appreciated
it. And Matt Byung had a question that was, I think, relatively standard, which is good. And he says, when do we select which type of counter electrode to use, whether mesh, plate, or wire? I also read somewhere that the surface area of the counter electrode should be larger of that of the electrode. He means working electrode. So why? So the counter electrode, you're correct. The counter electrode should be a larger surface area of the working electrode. And the reason why is the counter electrode maintains charge balance in a way. That's one way to think about it. It applies the potential between, like, to drive current, the counter electrode applies a potential between the working and the counter. And that's just from the circuit system. And large counter electrode areas are utilized so that there is no limitation in the current flow. You can imagine if you have a very large working electrode area and you want all this current to flow with larger current areas, you have more, or larger area electrodes, you have more current that'll flow. And you don't want to limit the current by what's happening at the counter electrode, because that will be the thing that limits you. So that's why the counter electrode is generally larger. And that's why meshes and plates and wires tend to have a larger surface area than the working electrode. So that's why, hopefully that explains why counter electrodes are so large compared to working electrodes. He also has a quick follow-up. I think it's a quick follow-up. Maybe it's not a quick follow-up because I haven't read it. Also, another experiment, 2 electrode system, we found that my solid polymer electrolyte is responding well to CV, whereas is not responding to GCD. Why is this happening? What is GCD? Do you know what GCD?
GCD is galvanic. What is it? Hang on.
Google is giving me greatest common divisor, which is not, let's see, GCD electrochemistry.
Yeah, it's sorry, I'm not coming up with the name of the acronym here.
CV varies
Yep.
the potential against time. GCD is
Galvanostatic
applying-
Charge-Discharge. Is that?
Yeah. Oh, I guess
that's-
it
think
is
that's just it.
galvanostatic charge.
Yeah.
Okay.
So
I guess
what
that would definitely-
range of amps per gram current is better for galvanostatic charge-discharge cyclic stability performance measurement? Well, first of all, it depends on what you're after, but generally speaking, if you're just trying to do galvanostatic charge.
Oh,
Okay, so I was
Thank you,
right.
Rice.
Or I got it eventually. It took me a minute.
Yeah. So many acronyms.
Yeah, I studied batteries. I didn't really use that acronym in particular. I mean, I would say like charge discharge experiments, whatever you
Yeah.
want to say. But there's a number of different ways people do stuff. I think with supercapacitor, it's also different than batteries. Batteries, you're typically looking at like 2C, 5C is like the fastest you would do, something like that. So, well, as far as the range value amp per gram, it depends on what your capacity of your battery is, right? I mean, if your battery is a 1 amp, amp hours per gram, we're talking about different units, amp per gram or amp hours per gram. I'm used to like amp hours or milliamp hours per gram or something like that. And if you're asking about C rate, again, it just depends on what you're like. There's different kinds of experiments. Some of them you like start slow, like C over 10, which takes 10 hours to charge or discharge, and then you step it down, you go faster and faster and faster, and then you go back to your slow and see how much is recovered, or the other way around, you start fast, you go slow, you go back to fast, and you see if it recovers its capacity. That's a kind of test. I guess I don't have a simple answer for that in particular. It depends on what you're looking to study. Like long-term stability, you're probably not scanning that fast. If you're trying to see how it degrades, you might be scanning very fast on purpose, something like that. But you might be asking a slightly different question. So,
and I'm wondering, also just talking about galvanostatic charge discharge, why would it be the case that CV data looks fine in a solid polymer electrolyte while galvanostatic charge discharge does not look good, or it's not responding?
Because solid polymer electrolyte.
Yeah, this is Matt Young's.
Yeah. You found it your solid polymer electrolyte. Well, what's the Faraday system?
All he's described is that he has a solid polymer electrolyte. I'm assuming that he has some redox species in there, but maybe he can elaborate.
Yeah, so I mean,
he's okay. I found that when I increase the scan rate, there's a lot of distortion, whereas slow scan rates, signal to noise is very large. Why is this happening? So when you increase the scan rate,
do you mean that there isn't a lot of distortion, whereas lower scan rate? So, oh no, signal to noise is large, which is good. So lower scan rates. Yeah, so you're saying that when you go slowly, it's better.
Yeah. And
I assume that's what you mean.
yeah, my thought, it has to do with filter settings of your potentiostat, because if you think about how fast you have to sample, like if you want to get like, I'm just going to make something up, but like if you want to get 10 data points a second, which is I think slow for CV, but 10 data points a second, it's okay. Okay, 10 data points a second, as long as your system, your potentiostat, and the electronics are reading quickly enough, you'll have no problem with that. But if you're measuring something very fast, like in a very fast, when you're using a very fast scan rate, there's a good chance that like, oh, the rate with which you're measuring things has to be much, much faster. Like now, all of a sudden, you need to measure 10 data points per millisecond, because that's now the size in your scan rate. And actually, if you're using Pine Research potentiostats and software, you can even do this. So I don't have actually I do. Well, Neil, could you, if you go to Aftermath, and then share screen, you have the WaveDriver 200.
I do.
hooked up.
It's hooked up to a resistor right now. What do you need me to do with it?
Well, if you just go to CV and hit autofill
Mhm.
just to get, and then share screen.
Yeah, I'm sharing now, I think, anyway.
Yeah, so right now you can see the sweep rate is 100 millivolts per second. If you go to the filters tab, just click on filters tab. It will say it has it set to automatic, but it has like, which is good, set it to automatic is fine, but it's like 240 hertz for the stability filter. And then for excitation, it's what's it say? It says like 65 hertz. Okay, if you go back to the CV parameters, keeping everything back, so keep it to automatic. But then if you change it to 1 volt per second or like 5 volts per second, and then go back to filters, you'll notice that.
Oh, I probably need to change.
Yeah, you need to change it. If you change it to automatic.
No, they changed.
They changed. So now it's like, okay, now it's 12 kilohertz, right? So this is just showing you that if your potentiostat isn't adjusting the stability filters and excitation filters accurately,
yeah,
then when you have faster and faster scan rates, you're going to have more distortions in your data. That's one possibility.
Most potentiostats probably do something like that, but I don't know. I mean, we can only really speak for our company, right? But we also have the ability to, you can, if you want to slow everything down a lot, you can just set this filter here and whatever. Yeah. And you can also set these filters to anything you want. There's options in here, but you can also just you can set your software filter to just slow everything way down. Yeah. You can overly distort your data if you overly filter.
Yeah.
So it kind of goes both directions, but if your potentiostat or your software has filtering settings, sometimes just troubleshooting with those and playing with those can help. But it's hard to
hopefully that helps map down.
Yeah. I want to know if there's a perfect way to make catalyst ink using MOF, which is metal organic framework, as a catalyst for CO2 electrochemical reduction. And
then she also has a couple of follow-ups. Also, just FYI, we've been streaming for about...
Yeah, we'll go for about 10 more minutes.
Just 10 more minutes.
2 hours will be about the cap, I think. And then if there were any other questions, join us next week. We're going to do this. This is going to be, we'll try to do this Fridays at about 1 o'clock Eastern US time. This will be our weekly Ask Us Anything About Electrochemistry. So we do appreciate everybody joining us.
And sometimes you can always tell, we're going to put like an announcement on the YouTube channel, and then what we're going to do is we're going to change it. So, but that'll give you a sense hey, an upcoming live stream is happening. So just keep that in mind for the future.
So first of all, I'm assuming with the metal organic framework that it's some sort of powder. Most of these catalysts that are used are powders, they're nanoparticles or something like that, but they end up being like some kind of powder. And so when you're making an ink, let me also just back up by saying one very general thing, which is that the perfect way to make catalyst ink is to trial and error that thing until you get it right.
Mm-hmm.
Unfortunately, unfortunately, a lot of your answer is trial and error. But I'll give you a few tips and tricks as you give it a try. And because your second question is, what is the proper way to use carbon paper for coating catalyst ink? Is there any pre-treatment needed before using it? Sometimes people will do stuff. It depends on what your system is. If you're doing, for example, alkaline or something, sometimes people will soak the carbon paper in KOH, or you'll soak it in acid, or I don't know. Sometimes you'll soak it in something, and that will help. I can't think of specific examples, but carbon in particular is it's hydrophobic. So if your ink is aqueous, sometimes there's ways to change the hydrophobicity or hydrophilicity, right, for that matter, of carbon paper.
You can use Tritenex solutions.
Is that a thing? Yeah, that's
my lab used to use
that messes with the surface
tension. And
it makes it more hydrophilic, right? Is that right? Or is it the other way?
Yes. Yeah. So
I think so.
Because my lab was doing they were on metal surfaces, Tritenex.
Okay. I've heard of that and I haven't used it. What is it?
It's so
is it a liquid?
Yeah, Tritenex is I think it's this polymer. Mm-hmm. And what we would do is we would do I didn't actually work with it that much, but it was you did a 1 to 1,000 or 1 to 100 dilution, used a super small amount of it. But we were making self-assembled monolayers on gold surfaces. So gold metals, very hydrophobic. Tritinex methanol made it hydrophilic. All of a sudden,
it changes the surface.
its
Some of
surface
them they
breaks
like,
surface tension.
add a hydroxide group or add some hydroxyl or add something that, makes it more hydrophilic. So that's the first thing, is that it isn't always necessary for pre-treatment of the carbon paper, but sometimes something like that might be helpful. The second thing is that with your ink, again, it really depends. It depends on what your ink requires or consists of, right? So the solvents could be water, could be an alcohol, could be a non-aqueous something like NMP or I don't know, DMSO or like there's all kinds of different solvents that might be required for your ink. So that will likely affect whether the hydrophobicity or hydrophilicity of your substrate, carbon paper in this case, matters. The second is that there's just so many different, and without knowing anything about your exact metal organic framework or anything like that, I can only give general advice. But having well mixed ink, people do things called the Dr. Blade method. There's fancy setups for this. There's crude setups for this, but it generally involves spraying an ink with so here's your substrate. Try to get the camera to my hands, and it's like a blade, literally, and it's depositing ink as it spreads over the surface, and so it spreads it in a very uniform way. And they make there's devices that do this in a very controlled way. Otherwise, with you doing something like that, you're getting like a blade and you're dumping some of your stuff and you're just spreading it out with a blade, which you can do. It's less, it's harder to do manually than it is with a thing. So that's a possibility. The other thing that you literally can do is buy art store paintbrushes.
Yeah.
Get a little vial of your thing. You get people do this for fuel cells, for example, like membrane electrode assemblies. You get a little vial with your carbon, your platinum on carbon, in your ink, and you dip your paintbrush in and you paint your carbon paper, and then you dry it or heat it. Sometimes you heat it to evaporate the solvent, and then you mass it. So you see how much you got on there, and you got to paint it again because you only get so much or whatever. So that's the process, is literally painting. And then the other way that you can try is, it's another art thing. This is really arts and crafts. This is not science, by the way. But it's something I did actually when I was making battery anodes when I was in graduate school. It's like a spray gun. It's like the art ones they use, but it's like a little metal spray gun that they use if you're doing graffiti or something, or
just spray paint.
But it's a smaller thing.
It's a smaller
it hooks up. Sometimes you hook it up to like a cylinder, like a gas cylinder, and that provides the propellant. And mine had that. It had a small little bucket. It's like a metal thing. It's like handheld, and it had like a small metal reservoir. That's where I put my ink, and it couldn't have held more than 5 milliliters or something. And you put it there, excuse me, and then it would spray, and it would I would just sort of, you put your carbon paper, tape it on a wall some distance away, right, with plenty of cardboard or something to capture the excess, and you just and you spray it, and it makes a nice kind of even film. So that's another thing to do. Those are different ways to kind of get the ink onto the carbon paper. I haven't really talked about preparing the ink. That is really just trial and error. Exactly how much ink to solvent ratio, what the solvent should be, how do you well mix it? Do you sonicate it? Do you stir it? Do you let it sit for a while? All of those are just trial and error, or find things in the literature that help you with those kinds of formulations. But this is really just an arts and crafts project, because you're eventually trying to end up with a nice uniform film that's of a desired thickness and mass. And that just takes time, practice.
We're almost out of time. There's one last, I think this will be the last question we take from Yanni. And he's asking, he's a chemical engineer working on electrochemical processes for CO2 reduction. And he's trying to isolate a specific surface area of 10 centimeters squared for both anode and cathode. Do we have tips and tricks for accomplishing this? I think we would need to know a little bit more about the system, because, for example, if you have some big surface area anode or cathode, you might just buy an O-ring where it's got a 10 centimeters squared area, slap it on, put some kind of compression fitting on it, and
Yeah.
that's the only area that's exposed to solution. That's one way to do it. I don't know, you can get very good with I used to use like Torseal epoxy as a thing to like block off, basically gluing off areas that needed to be exposed to either vacuum or it's resistant to many solvents and electrolytes. You can try and measure that, but it sounds almost like a mechanical engineering type of thing, just isolating a certain surface area.
Yeah. And they, if it's like a fuel cell kind of a thing, for example, with anode cathode, like fuel cell hardware typically come in like 5 square centimeter or 25 square centimeter, like gas diffusion layer or like bipolar plates or whatever they have. They're usually like, they'll come that way. And it's just done with the hardware, with the O-rings or with the sealing, or the size of your carbon paper is cut in that way. So I mean, the tricks for doing those things, like Alex said, an O-ring that has that particular surface area will help. Sometimes isolating with like Teflon tape can help, or other sort of insulating tape. You can kind of like, you wrap or line, right, whatever part of your electrode or hardware or conductive part, I guess, with something insulating like Teflon tape that won't, and then so whatever is exposed is just the 10 square centimeters, which is something like three and some change centimeter by 3 centimeters square, something like that, right? So you could make almost like making a mask with Teflon tape that might be it. But some of the answer to this too is just whatever the specific, we would have to know more about the specifics of your experimental setup, of course. And, other than that, those are sort of the generals that we can provide you here. I do see there's a couple of things. Thanks for the comment, man. We appreciate it. Glad. Thank you for coming. Solid polymer. I'll just sort of, you mentioned the GCD is not responding. Maybe there's no charge carriers.
But if it's working for cyclic voltammetry.
Well, it depends on what working for cyclic voltammetry means. I mean, if you're seeing a lot of peaks, there should be some Faradaic process. It's just in my I haven't found a lot of systems for which CV and charge discharge both work ideally. Like if charge discharge works, then only the slowest possible CV will work usually. And that seems to be like what you're describing, because you're getting some slow works better than fast. The signal to noise is better. But I don't know that I know much more than without looking specifically at your system. But I do think, or it could just be that you have a very low capacity. And so the charge discharge is working, but you're charging too quickly. Maybe it's getting to the lower or upper potential faster than you expect because your capacity isn't actually all what you think it is, for example. So you might need to decrease the applied current positively or negatively, or set your cutoff trigger potentials a little bit differently. But without any more information, that's the best that I can kind of give you.
Yeah. I think this is the one last question. But I think the answer is going to be very simple. Is that we don't know enough about ionic liquid gates. And so I don't know what the applied voltage is. I might recommend, like, if you hook your system up, do an open circuit potential and just see what you get. And
if you're asking what the limit is, I mean, ionic liquids can usually go 2 or 3 volts. They can survive really high voltages.
Oh, okay.
But I mean, the answer to that is which is something that I think you talked about, like one of our first live streams. It's get an electrode and set scan limits and just scan. Scan from +1 to -1, then +2 to -2, then +3 to -3, then +5 to -5, whatever. I mean, it's not going to get that high, but like just keep increasing your scan limits until you start getting crazy current deviation. And that will determine how far you can go in either direction. But ionic liquids are one of the kinds of systems where you have the most leeway. They're quite stable and they have no vapor pressure whatsoever, but they have to be used in a glove box strictly, because as soon as they're very hygroscopic. So as soon as they start getting water in them, they're a complete mess.
Okay.
Okay, I think we're gonna have to call it because we can
Yeah.
kind of go forever as
Yeah,
questions.
yeah.
Anyway,
For 2 hours, it's good.
yeah, we really appreciate everybody who joined us today and provided questions. I'll be honest, we weren't sure exactly how many we'd have and whether we'd just sit here talking about 90s movies or something
Yeah.
together.
Yeah.
But you all kept us going for 2 hours. I hope it was helpful for everybody and useful. We really appreciate it. We're gonna try to keep this up as a weekly thing on Fridays. Maybe not always both of us will be here, but we'll try to keep a weekly kind of ask us anything on YouTube appointment. So spread the word around if you know others wherever you are. We would love to have anybody join us. And I suppose thank you again. We'll see everybody next week or whenever we see you. Yeah. Thank you very much.
Take care. Bye, everybody.